Hello. This is my first keynote. I do a lot of public speaking, but everyone has to opt into my talks, so you're my first captive audience, and you have no choice. Is it showing now? Okay, so today I'm going to be talking about walking into Mordor, the history and future of DevOps. So a little bit about me first, if this works. Or maybe I need to walk closer over here. Aha, I will stand on this side of the stage. Okay, so I am from Des Moines originally. I work for John Deere Intelligent Solutions Group. We have that fancy new building you see that we're building out in Urbandale. It's going to be pretty cool. As Tim said, I've worked in this town for a while. Prior to John Deere, I worked for the kind of mystical and legendary GeoLearning, which like a third of the people in this crowd probably worked at. And I'm on Twitter and GitHub as Ryber, which has been my handle on computer systems since the 80s. Maybe this is, oh, okay. So this is gonna be rough because there's a lot of slides. So as you know, you don't need to know much about Mordor for this talk, only that it's a horrible place that you don't want to go. And apparently, according to internet memes, you can't simply walk there. But software developers and people who work on software systems often find themselves they wind up in Mordor. It's just kind of where we end up. And it doesn't matter if you're doing waterfall or agile, at some point or another, you're going to wind up in Mordor, and you got to have to figure out how you got there. Now, that can happen on a micro level. On any project, we'll wind up in Mordor at some point or another. It also happens on a macro level. Computers, software systems in general, our entire ecosystem, I believe right now is in a very dark place, a low point. It's going to get better, but right now things are a little tough. So we're going to talk about, how do we get there? Where are we at right now? What does it look like when we're going to deliver software today? So let's step through that a little bit. Do we have another clicker that maybe works better than this one? Please be patient with our technical difficulties. It's very slow. Nope. Okay, so we have a developer. A developer has an idea. This one is not really working either. Can I? How about I stand down here? Is this okay? This works pretty good. Sort of. Maybe Tim, you're in the way. Okay. Everyone good now? All right. So you got an idea, you got to write up your requirements, so of course we're going to put it in Jira because that's what people do, right? And then I actually have to write my program, and I'm going to pick Haskell because I'm a hipster like that. And then we got to put the program somewhere, so we're going to check it into Git because, again, that's like the thing everybody uses. But I can't just store Git on my local system, so I got to check that in, push it somewhere, so I'm going to push it to GitHub. Then we need to build it, right? So we need to check the code out of GitHub, and we're going to go build it and do our tests and stuff, and we're going to use Jira for that. But Jira you can't just have one Jira. The Jira has to have a bunch of little Jiras. Not Jiras, Jenkins. The Jenkins will then do a whole bunch of different things. They'll run tests. They might do scans against something like Black Duck or Veracode. And then eventually it'll package stuff up, and then you got to store what you were doing. And so you're going to stick it in something like Artifactory. And then at this point, you may have been able to do all of this even on your local system, or maybe just something that's not super important. But now we got to go deploy it, so it's got to get real. So the first thing we got to do is get out our credit card and give it to Jeff Bezos. There's Jeff. Now, we're going to go and build and deploy our system. So we're going to get out Terraform. By the way, to any of the vendors that are sitting in the room, I may or may not reference your product on these slides. I apologize in both cases. So then Terraform is going to go and it's going to store a bunch of keys and stuff in Vault, and then it's going to use that to build out our environment in Amazon. So we're going to have maybe a RabbitMQ, maybe a Redis cluster, maybe a Postgres database. Then we're going to go to Terraform, because of course we have to go to Terraform. People keep using that word, and I felt like this was the right place to do it, but I'm not really sure what it is, or Kubernetes, I'm sorry. So then Kubernetes is going to make a whole bunch of Dockers. We're going to put the Dockers inside of EC2 instances. And then we're going to slap a bunch of Kong sidecars on the side of it. And then it's going to go. I know. Maybe I need to step. OK, I'll do it right here. So then going to go up to an Nginx load balancer, which goes out to, got to configure a bunch of DNS stuff. We're going to have to wire everything together with Okta so everything has client credentials and all these microservices can start talking to each other. And then finally, it'll go out to a browser and to a person. And it's our customer. Now, this isn't enough because the developer, me, that's me up there in an Andy Warhol wig that I did from a previous talk. I need to see stuff. So we're going to slap some log stashes on those. Those are going to write to a Kinesis or a Elastic. The Elastic gets fronted with Kibana. And then boom, there's me. And then unbeknownst to us, inside every single one of the pieces of this is a cryptocurrency miner. So there's blockchain in there, which is good because marketing will show up and say, hey, we're using blockchain, right? Because that's the future. And we'll say, yes, we're secretly mining Bitcoin. Now, look at this. No rational human being would create this by, intentionally, but we do it all the time. This isn't an exaggeration. There's probably multiple people who have this exact thing going on. And the sad thing is, you look at all of this and look at all the different pieces in it. Look at all the different languages you need to know, everything that's got to fit in your head. I just counted throughout this, you got Bash, Haskell, Groovy, Terraform, it's just like a custom language, and Jenkins is like some weird Groovy. Postgres, Elastic, YAML, XML, JSON. You got to know all of those. As a developer, as a DevOps person, you have to know every single one of those things. And for some reason, we've all decided that YAML is our favorite. And I don't really understand that. The YAML spec is 24,000 words, over 24,000 words long. It's longer and more complex than XML, which is the thing everyone used to say they hated. It's way bigger than just JSON, or TOML, which is a very pleasant little markup language, if you ever want to check it out. The Python language spec is 38,000 words long. So we are configuring ourselves with a markup language whose mysteries are all in white space and is almost as complex as a full-blown computer programming language. Maybe you should just use Python. It also has the white space thing going on, if that's what you like. There's also, all of these things require authentication, right? I have to log into all of them. And so I have to remember, maybe I got my Okta set up so I can do single sign-on with all these things, but that also means that I need to configure OIDC or SAML for all these different things. And this isn't really so much just a criticism of this in general. This is our problem with the entire internet at all. Like, we as a profession have completely failed society with what we've done with usernames and passwords. And I don't know what the answer to it is, but I know that what we're doing is really bad. So you got to think of this is more cognitive load. Now I got to have something to manage my password so I can get in on all of these things. And of course, every single thing on this slide can be replaced by something else that is slightly different but is basically the same. Not just one, but probably two or three. You can give your money to Microsoft instead of Jeff if you want. Also, almost everything on this screen was, at one point, at some company, was handwritten by some software developer who just wanted to do it by hand. I guarantee you, somewhere, someone has coded their own version control system, someone has created their own cloud made out of Perl scripts or something. And it's happened, and you'll find it. And I feel bad for people. I like to just go work for someone and work for a long time and really get to understand the domain, so I don't get exposed to as much as people who contract and go from one place to another. Because you could have any combination of all of these things, and it's going to be different. You know, this group's using Mercurial, this group's using Drone, this group's using whatever. And you got to know all of it, and it's all a little bit different, mostly the same. So, and that's how we got into Mordor. So that is where we're at right now, is Mordor. So how did we get here? What is the history? And I find that when I look around a room full of developers, a lot of times I'll walk in and everyone's under 30. And that's been the case for a long time. And that's not because those of us that are a little older, you know, we went anywhere. We're still here. But this pool of software developers is growing at such a rapid rate. I think I read that every 10 years, the number of software developers there are in the world doubles. And so there's just this enormous pool of young people, and so we lack any kind of shared history that can be distributed. So I'm going to give you a history lesson on running software. So yesterday when we were having the bench thing, and the first topic was how do you define DevOps? I think a very simple definition is the art of executing software. Anyone can write software. Executing software is much harder than writing it. So let's go back in history, and I'm going to start off with a couple of slides that are kind of obligatory because, you know, if I don't say it, then someone's going to say, hey, you forgot about so-and-so. And the first one is Ada Lovelace and Charles Babbage. So we're just going to go back to the very beginning, the very first computer programmer and the very first hardware dude. And they were great. It's a great story. If you don't know the story of Ada Lovelace and Charles Babbage, read it up on Wikipedia. They were so steampunk, it's cool. And the problem is Charles Babbage never actually produced a computer. So Ada Lovelace's programs couldn't actually run on it. So they were basically like the world's first R&D department in that they didn't actually produce anything. But they're still cool. We still love them. Next, because we're in Iowa, I have to mention the ABC computer from Iowa State University. How many Iowa State grads are here? All right. And as you know, as you're drilled in at Iowa State, the ABC is the first digital electronic computer, right? We have like a patent on it or something, or we broke someone's patent. The ABC is great, did a lot of cool things, had the first kind of, basically its form of memory is the same as what we use today in a way, and has a lot of other cool aspects to it. Its main problem is it's not programmable. It can only do a series of linear equations, a set number of the same type of linear equations over and over again. It's not a general purpose computer. And that goes to the ENIAC. So the ENIAC was created in 1945 during World War II. It was first used to calculate theoretical aspects of making a nuclear weapon. It would later served for another 10 years, creating ballistic graphs and charts, you know, for figuring out artillery. It was programmed almost entirely by women. The first software development team ever, professional software development team of people who came in and got paid to do software development were these women: Betty Jennings, Betty Hoberman, Kay McNulty, Marilyn Metzer, Frances Spence, and Ruth Teitelbaum, if I pronounce that right. They practiced pair programming because if they got something wrong, you'd get a missile in your house. And also the way that the ENIAC was programmed, if you got something wrong at the very beginning, you'd have to rewrite basically the entire thing. And writing a program for ENIAC basically involved moving a bunch of switches manually around. They were basically doing, you know, binary trigonometry with a bunch of switches like that. So they were in charge of maintaining the ENIAC and doing the programming. So they were doing the dev, they were doing the ops, they were punching Nazis in the face with math, and they were super awesome. And this is the beginning of our history. Now, women would continue to be dominant in software in the programming field throughout the 40s, 50s, 60s, and into the 70s, once dudes figured out that you can make a lot of money doing it. But there's a lot of limitations to this kind of computing. What it gave way to was mainframes. So IBM and Digital and other companies started making mainframes for corporations. And this is another great picture of some other women that were on it. But mainframes have big limitations. They can only do a set number of things. The ENIAC really could only run one program at a time, and then you'd have to reprogram it. And it took a long time. The programs weren't really reusable because you basically had to recreate them every time you wanted to do it. And later on, as mainframes evolved, we started to evolve things like written programming languages, and we could store those on tapes. A lot of times, though, these systems could still only do a set number of things. They got better, could do more than one, but they couldn't do a whole lot. And you would often have to be time boxed to it. So you would get put in a request and say, I need to run my program. And they'd say, you get to run your program between 2 o'clock and 3 o'clock on Thursday. And you don't even know if your program is going to compile, right? If it was something that compiled. And you'd get you there for your time, and you'd run it. And if it took too long or if it broke, tough. Your hour was up, and you had to go back to the drawing board and request a new time. Imagine doing TDD like that. It would have been really, really hard. There was also the possibility that you could get bumped. There was a story that I saw online last year, and I searched and searched and searched for it, and I can't find it now. But it was about someone at MIT, I believe, or it was one of the Boston universities, and IBM had loaned them a bunch of mainframes. And the deal was they could use the mainframes all they wanted, but if the president of IBM wanted to bet on boat racing, that he got to use the computers to do his calculations. And so you could be a grad student with a very important project, and all of a sudden the president of IBM wants to do boat racing. He got to use your computer. And this is kind of the world we live in. Now, they got better. We started to do virtualization. Mainframes today can do a lot of things, but they're still really kind of fixed, right? They got a certain number of cores. They got a certain amount of memory. And they can only do so much at once. And they're also really, really expensive. And if you wanted to get a new one, you would have to put in a request. And IBM would actually have to show up and install it. And it was like a big deal. If you wanted a cheap one, a very small mainframe, a PDP-8, was about $30,000 and would have to be hand-delivered and installed. PDP-8s are really cool, though, so I would really love to have one. So how do we fix this problem? This is the problem we have, limited resources. We fix it with microcomputers. Let's make small, tiny computers, and we'll just make a ton of them. And so that's what we did. And so here's our friend Steve Jobs. This is the era where I started programming as a child. I had a TI-99-4A, and this is a replication of my first computer program ever, which almost everybody who programmed in BASIC in the 80s wrote that exact program, replacing your name. But these also have limitations, right? They have very fixed resources, and distributing programs commercially meant you had to distribute it on physical media. We didn't have an internet. You couldn't download things. You had to go to a store, and you had to buy a disk or a cartridge or something. And that also meant that your program, if it went on a cartridge like this, had to be perfect. It could have no defects because there was no way to patch an Atari 2600 cartridge. Didn't exist. Everyone would just have to enjoy your bug for the rest of your life. If you worked for a commercial company and you were selling like enterprise software and you were a computer programmer, the way it got patched was you flew to every customer and you patched their computer it was very common all the way up to into the 90s that if you worked for a big enterprise company and you were if you worked for a company that was selling enterprise software and you were a software developer, you were probably going to have required some amount of travel time to be able to go to clients and install things in their private data centers. Because of the fragmentation of these systems, the idea of writing once and it executing on all kinds of different platforms wasn't really, it was more of a guideline. Porting basically meant rewriting a program to match the hardware specs of different things. So here you got the famous Donkey Kong. This is Donkey Kong, the original Donkey Kong, Atari 2600, Texas Instruments, Commodore 60, or that's Atari, or Apple, and I believe that's Commodore, or one of the ways the others. Each of these, you can note, look how different they are. And that's because they were basically rewritten. Someone just rewrote Donkey Kong. The thing is, they had a template for what Donkey Kong was supposed to look like. So it's a little bit easier. And even if you say, oh, Ryan, what about once we commoditized everything? Everyone went to PCs and Intel processors, Microsoft operating systems. But the fact is that during this time, things were changing so rapidly that almost didn't really help that much. You couldn't write a program for a Pentium or a 486 and have it run on a 286. Probably wasn't going to run just because as software developers, we will take up all the resources we can. And the resource constraint was moving so fast that you were basically buying a whole new computer every couple of years, and you'd probably have to buy a whole new version of the applications you wanted to use. So you just look at the difference over time. So it's my first computer, which had a 4 megahertz 16-bit processor and 16 kilobytes of RAM. And jumping up from 16 kilobytes to 4 megabytes, that was massive in like 2000. I was like, 4 megabytes, I could put all of King's Quest in RAM. And and then up to 2001. And today, this laptop, which is running right over here, has a quad-core 2.3 gigahertz processor. Our processors are now so fast, we don't even bother talking about them anymore. Like, I don't know the last time I actually paid attention to how much CPU. I do pay attention to RAM. I have 16 gigabytes of RAM. I'd like more, please. I don't care so much about hard disks, though. So how do we solve this problem? The internet. The internet, Microsoft felt that the internet was an existential threat, and it was. It killed the 90s Microsoft, and we now have a kinder, gentler Microsoft, which is much more pleasant to deal with. Because now we can write programs, and they literally can run on almost any computer, and it's pretty much the same. And, I know there's some UI people here in the room that are probably going to complain about different browser types. That's nothing compared to like having to compile something to different CPUs, right? So this is what it looked like in the beginning. I started off as a professional software developer in the 90s during the first .com boom, and this is pretty common. We literally run our production servers out of a closet. And they were all artisanal servers, all handcrafted. And so we'd jam like a whole bunch of Cold Fusion web applications running on one server. The database was on another, hopefully. But I have seen it where someone installed the database on the same server as the web server. We'd have our own mail servers. None of this is terribly encrypted. There's a backup in that all the disks are getting backed up to somewhere. There's no backup servers per se. So it was very common, if you had an outage, that you would have to go get a whole new server, right? This is one of the startups I worked for in Des Moines. We actually took an outage because we moved offices. And we had to take the server out from under the architect's desk and drive it out to the new office and then plug it in under his new desk. And luckily, DNS changes at this time were so slow that the DNS change was slower than us driving it. So it wasn't really that big a deal. We did it at night. We didn't have a lot of traffic anyway, so it was really common back then. Everyone talks about how many 9s I got these days. It would have been impressive if you had 2 9s. That would have been like amazing. Most people had 1. Things were down. It was very, very common for anything to go and have some big splash page up that says, we're currently working on upgrading our systems. And it would be like that, for the entire weekend. And when I'm talking about like banks and big systems that you were expecting to use, pretty common to have big outages. So let's talk a little bit, let's do the same exercise, 1999 style. So I'm going to write my requirements in Word, and I'm going to write everything in PHP, because that's what the cool kids were doing at the time. I'm going to save it in a folder, and if I need to make changes, I'm going to make a copy of that folder, and I'm going to call old. And then I'm going to write all the new stuff in the new folder. This all gets backed up. That's version control. Then I'm going to go to CompUSA to buy the production server. And while I'm out, I'm going to stop at Tasty Tacos. And then I'm going to take it back to the office, and I'm going to install all the software on it off of CDs. Oh, wow, look at that. You guys, this thing like wants to go not at all or like all at once. So then we're gonna set up our servers. They were big, beefy servers. These things were huge. We spent a lot of money on them because setting these up is hard. So you wanted to make sure that your server was going to last a long time and you were going to get the most use out of it. So we would buy really big, really expensive servers. Probably not from CompUSA when we got the really big ones. Then we'd be ordering them from Dell, but they'd still be shipping them to like your apartment or something like that. I had a friend at a company in the early days of Geo, and our data center was in Ottawa, Canada. And so our sysadmins were up there. And we had a big new system we needed to install, and so we ordered 7 Dell servers for the web servers, 2 database servers, and shipped them all to his house, and he set up the entire thing on cinder blocks shelves in his apartment in Ottawa in the middle of winter, kept his windows open for cooling, and then you get all this stuff set up, because you don't want to do this in a data center, because you're not going to see the sun for like long periods of time. You're going to go in early, you're going to leave, and you're never going to see the sun. And they're cold and they're dark, and there's weird security guys who want to talk to you, and you're just trying to get your job done. And so you do it all in your apartment, and then you put it in your Honda Accord, and then you drive it out to the data center, and then you install it in a cage, a literal cage. And it's weird how many people, young people just coming out of college, like don't realize this is what data centers actually look like, or what we did. But you'd have your own little private cage in there with your power coming down. Then you would buy the domain name from Network Solutions, and you'd pay like $200 for it, because they were literally the only person you could buy a domain name for. You didn't have GoDaddy or $15 domains or anything. They had a monopoly. Prior to them, you'd just email someone in the government, and they would give you it for free. Then you would FTP all of your stuff onto the server from the programmer's desktop. Maybe if you were fancy, you could use SSH and Vim. But actually, most of the time, I did everything purely through FTP. And there was some, like BBEdit would basically let you open a file via FTP, edit it, save it, and it just pushed it back over FTP. Not secure FTP, by the way. This is just regular FTP. You'd set up something like Apache, and your PHP server, and your MySQL database. Again, all done by hand, all artisanal, never quite the same way twice. And then you do the same thing with your DNS and your magical routing, and it go to the browser, and then you get rickrolled. And if you're lucky, the whole logging part might exist or it might not. A lot of things, like I remember when logging first even showed up, and I was like, things can log? Like, I can get a trace of something that happened on the server? Early versions of PHP couldn't even log at all. Same with Cold Fusion, which was really popular at the time. In the startup scene, Java could do logging, but that was like serious programmers, and only like enterprises did Java. And Java was weird anyway. So, this is the time when we started separating, right? We have stuff that's clearly has to do with the server, and you have the stuff that has to do with writing the program. And that's when we started to split. Before this, it was really kind of the same people doing the same stuff. And if you were a startup, at the time, you were probably doing both anyway. But then as you grew, you started to see this split between operations and development. And because a manager could say, this person is just going to go do servers, and this person is just going to write programs. And there was always some kind of crossover between the two. Like, I was always the person who was going to configure the PHP server. I didn't trust a sysadmin to properly configure my PHP server. And similarly, the sysadmins aren't going to trust me to go into a cage and plug wires around, which is wise because I'm really bad at networking stuff. So how do we solve this? Virtualization. Virtualization is what saved us from this life of having to do everything by hand. So we can now just magically spin up a server and on another server. We still have limited resources, but now we have these magical little servers. And we've slowly been evolving since then, since the very beginning of that. And this is necessary because the problems we're solving are infinitely more complicated. We couldn't possibly do stuff like Google Maps by building the stuff out by hand. It's too complicated. There's too many pieces. You saw the slide at the beginning with all those pieces. Those are all necessary. Everything there has to happen. We couldn't do that wiring servers up by hand. We needed it. And you look at what the problems we were solving in the 90s versus the problems we're solving today. We're pushing all of these super hard, interesting, difficult problems. The fact that Google Maps can tell you which route is going to be better based on what construction is happening is on any particular day and knows about traffic patterns and stuff like that is absolutely amazing. And I would shudder to think of having to maintain that infrastructure by hand. So this is what the infrastructure looked like in the beginning. Like in the 90s, this is what we did. 2 web servers, 1 database. Maybe the database has backup, hopefully. As we grow, things get, we have more web servers, and then maybe we're starting to spin off other servers to do things, and it's starting to get more complicated. And then we get this virtualization, and we can move to the cloud, and then someone came up with, well, now that we can just spin up a server whenever we want, we could make our services really small, and we could have microservices, and the microservices can talk to other microservices, and it's getting even more complicated. And then some of the microservices catch on fire, and our Mongo database is filled with garbage, but it's okay because everyone's isolated, right? So that guy goes down and nobody else goes down, right? That's the way it was promised. And so we have this, and we have this, and we have to take both of them and we have to shove them in our heads. And there isn't anyone in this room who can works on a system of any complexity at all that can truly know all of the pieces of this. We all know little pieces of it. We can't know all of it because that's just too much. And so we're in Mordor. Here's a really scary thing. So I was at GitHub Universe last fall. This is a real number. In 2020, there will be 1 million unfilled software tech jobs. 1 million jobs that will just go unfulfilled. We're growing. Our profession is growing at an exponential rate, but the demand is even higher. The demand is insane. And so we can't keep up doing this, right? There's way too much of our brain power that's being eaten up by this, and it's not necessary, not in the long run. It's necessary right now. So what do we have to do? So this is the part where we're going to talk maybe a little bit about how do we get out of Mordor, right? The first thing we do is we must simplify. I looked at a few repositories, a few projects that I worked on. This is a microservice that I work on, and I analyze the commits. Of everything in it, 830 total commits, 266 were for a cloud infrastructure setup. That means that 37% of the commits had nothing to do with anything anybody wanted as a feature. It doesn't differentiate us in the market. Everybody is doing this, everybody's in the cloud, whatever. It's not necessarily means that I have a feature that's gonna differentiate me from my competition. So that's an awful lot of work. Now, this particular project has a little bit of drama behind it. So I looked at another one. I said, oh, that guy's drama. Let me look at a different one. I looked at a web application. And it's a little bit better. There's only 47 commits out of the 1429 that were with cloud infrastructure setup. There was 130 that had to do with CI, Jenkins files, test stuff. That's still 14% of that project that isn't really used. Again, doesn't differentiate us in the market in any way. That's too much. So I have this theory. It's called Ryan's theory of tool complexity. And it's not a scientific theory, and it has no scientific measurement. It's measured in ermigirds, which is basically how freaked out am I about what is going on and what I don't understand. So this is what kind of Java looked like. In the 90s, Java was just kind of cute, and everyone was like, oh, it's like Smalltalk, but it's free. And then all of a sudden, what happened here was that the dot-com boom stopped, and we went into, and all the people who worked at the dot-coms went to work for enterprise companies because all the enterprise companies decided, oh my God, we need websites. And they're like, you can't use that PHP, you need to use a real programming language. And so they said, well, let's use Java. And then Sun was like, let's strap on lots of frameworks to Java to make it not Java-y. And so we start out there. And then you look at a Java project from about 2005, and they are just like the worst things you've ever seen. And it doesn't matter who wrote it or where it was. The frameworks like EJBs and Ant, and it was all like everything splintered and exploded, and there's all these frameworks, and they were all competing with each other. And nobody really knew what was going on. And over time, though, through kind of the laws of natural selection, a lot of these start to get dropped. And we start to consolidate, and we start to get simplified. And so if you look at the Java infrastructure today, you can choose between like Jetty or like Spring Boot or Java Spark. And Spring Boot has a lot of those complicated frameworks in there, but it abstracts them and makes them all like part of some unified thing. And a lot of those frameworks just died. Nobody does EJBs anymore. And so things start to simplify and get less complicated. And you can look at any infrastructure and anything, and they all kind of follow this pattern, I've noticed. So you looked at, after all the cool kids were done with Java, they decided, oh, Ruby's magical, let's do Ruby. And Ruby got really complicated, and now it's kind of simplified down because all the cool kids jumped to JavaScript. Anyone who's doing Node.js or JavaScript, you are at peak complexity. You're at 1995, or you're at 2005 Java right now. And so if you're frustrated by React and NPM, and yes, NPM is not very good, has a lot of problems. It's getting better, and they'll all get better, and it'll all settle down. But if JavaScript seems kind of stressful right now, that's because it is. And CI is, and deploying and running software is the same thing. So we started off, we had only a few tools. We did everything manually. There was a lot of Perl. We suddenly introduced some tools for that. You started to see Puppet and Chef and Hudson, and people writing a lot of Ruby to glue stuff together. And that kind of evolved into where we are today. It kind of evolved into this. We're starting to see, we have this explosion of tools. There's so many tools to choose from. Again, they're all kind of the same, but they're all slightly different. And we're trying to figure out, we're weeding through this. Natural selection will pick which ones are going to survive and which ones aren't. And there's going to be consolidation, and things are going to eat other things. And we're going to wind up with a simpler framework where everyone just kind of gives up and says, yes, we're just going to use that thing because it's the simplest one, and it does everything we need, and it'll get less than this. But again, please don't make me do YAML. And so we're going to move to something that kind of looks like this. One is, I can almost get, this is my big prediction, that in 10 years, everybody's in here is going to be writing WebAssembly. And it doesn't matter what you're writing right now, Java, C#, JavaScript, it's all going to wind up getting compiled to WebAssembly. And it's all going to go out, and it's all going to run in the cloud on serverless systems that run WebAssembly. And that's going to be their only requirement. You make your thing, you give Jeff Bezos a bunch of money, and he'll run your stuff in the cloud. You look at like Lambda right now, like AWS Lambda, it's very simple. It's like a one single-celled organism version of serverless, and it's going to get more complicated. Not necessarily more complicated, but it's going to get more feature-rich than that. And we're going to start running entire applications, and you're not going to know anything about the server. You're just going to pay Jeff in like compubits or something. He's going to say, you used 50,000 compubits and owe me this much money. And you're not going to know what that means because you don't have to worry about or think about CPU, RAM. There's infinite CPU, there's infinite RAM as far as you're concerned, not as far as Amazon or Microsoft or Google is concerned. They have to deal with the constraint of resources, but you won't. They want you to spend as much money and spend as much compubits as possible. So they're going to make that all kind of a reality. And so what is this starting to sound like? Like we're just sending applications out to this thing that's going to run them and then give me back the results. And I don't have to think about necessarily the internal constraints of it. It's because it's very similar to mainframes. Basically, serverless is mainframes. It's the same thing, except you don't have to think about the constraints and you don't have to think about the time stuff. And you can think about these data centers that are going up. This is Microsoft's data center going on the south side of Des Moines. I don't know, there's like 2 buildings there. They're going to build 2 more. Facebook is out just north of Altoona. You know, they have at least 2 or 3 buildings there. These like data centers are your mainframe, the entire infrastructure. You know, you have these availability zones and stuff, which basically means there's 2 buildings, and the entire building is a backup of the other building. And eventually, you're going to stop thinking about all of these servers and stuff. And you're just going to send stuff in, and it's going to operate off of one of these, and maybe it talks to another one. So it's a very interesting future, the way we're headed. So again, 1 million unfilled jobs. Eliminating a lot of the complexity of all of our systems, that will be helpful. We'll have new things we'll have to worry about, but it should be fewer pieces. But we're still not going to be able to fill that many jobs. The universities aren't doing it. The universities aren't producing enough students. They couldn't possibly ramp up to meet the demands. So we got to start looking at other places. One of the ways we can help eliminate the amount of time each individual has to think about stuff is by using DevOps as a culture of collaboration. So if you have a bunch of teams and every one of them has their own little 2 giant boxes stuck in their heads and they're all reinventing the wheel, that's a lot of wasted work, right? You also don't want to have just one DevOps team telling everybody what to do. Also breeds a lot of other problems. What we want to try to produce is a culture of collaboration where teams can contribute to other teams and be responsible and help each other with different kinds of goals. And I look to the open source model for this. I'm a maintainer of a popular Java library, and I've found since doing that the way that open source software evolves is very different than the way corporate software evolves, and it's much more collaborative. And if you don't think that you're using open source or you don't think open source is that important, go look at your projects today. I looked at some of my projects that I work on. That Java microservice, that same one, compiled Java, 971 kilobytes, 70 megs of open source software that runs that microservice. And that's like Spring and all the Springy bits. A Java monolith that I looked at, this is a big application, has thousands of classes, still compiles down to only 29 megabytes of actual Java bytecode and has 273 megabytes of open source software in it. JavaScript's not much better. And this is an OSS library, so OSS libraries also use other OSS libraries. But you can see we don't crack 10% native code. So just keep in mind, 90% of your application is written by somebody else. 90% of your application is written by a distributed individual who's not doing pair programming probably. There's a different form of collaboration that happens in open source. But we talk about, oh, we need everyone to be doing, everyone needs to be co-located. 90% of your software is not written in a co-located fashion. It's written out of 20 different people's basements. So what are some of the golden rules for running what is called inner source? You can Google that. It's a term. There's some papers written on it. Again, don't mandate things. Mandating causes resentment and anger. Developers don't like being told what to do. It's just kind of our thing. And it's okay in your business to have multiple competing versions of the same kind of thing. Probably don't want like every team doing their own thing, but having a couple is healthy because then you can have natural selection, kind of pick which one is the winner in that case. You want to be respectful and kind and of people's pull requests. Realize that other people have different goals than you. So the open source project I work on is a HTTP client, and I get a lot of people who have different ideas about what it should do. And you got to keep an open mind that just because I don't think that that's the way the library should go doesn't mean it shouldn't. It doesn't necessarily mean I will approve it, but you need to be collaborative, and you need to realize that people come at you with all kinds of different levels of experience and all kinds of different levels of, a lot of them sometimes aren't even software developers. And in fact, there's a lot of people that are doing software development today that aren't traditional software developers. We'll talk about that in a minute. Try to have extra empathy if you're doing pull requests. Try to be extra kind, in conversations online with different people, because it can come off, sometimes you can come off as harsh. I like to use extra emojis just because I feel like it helps get my point across, that I'm not being mean and I'm trying to help you. And also have a code of conduct. GitHub, and I'm sure GitLab, will generate a code of conduct for you. If you don't, you can go take one from somebody else. And have contribution guidelines on how to do stuff. And then finally, don't be afraid to, there we go. You're going to need to write documentation and have good documentation, good examples of how to use your stuff if you want other teams to do it. So the idea here is that maybe there's one team that's really into Jenkins files, and so they've figured out a way to kind of box that up and make that easy. Maybe another team is really, really into Terraform, and so they're the team that's going to help other teams with Terraform issues. Maybe these are simple help documentation that different teams are writing, but you can distribute that, and according to what teams are interested in too. And so if you're going to make breaking changes, offer to help other teams, offer to maybe do the fix for them. And then finally, don't be afraid to throw away stuff. If an open source project shows up and it does what you're doing, but it's better, don't be afraid to throw your stuff away. Don't have an ego about it. There's very little code that I wrote there's probably no code that I wrote between 2000 and 2005 that's running today. It's all gone. Just let it go. So finally, we're going to talk a little bit about what we need to do to expand the pool of software developers. Obviously, we can't fill 1 million unfilled software development jobs with white dudes, right? There's always so many of us. And so opening things up and having your company be open to a lot of different people. And I'm not just talking about the obvious ones, right? Like, sex and gender and religion and all of those things, which obviously, we need to be cognizant of. But if you come at me and you say, Ryan, we got such a diverse team because we've got an African-American nerd and some women nerds, and we're all going to go watch Endgame together after the work, and we're all cool. I'm going to say, first of all, that's really cool, and I would like to go see Endgame with you. But maybe opening up the idea of what is a software developer, right? We can have different backgrounds and education and personalities. We don't all have to be this kind of nerd stereotype. And if you look at the Stack Overflow surveys, which is, take it with a grain of salt. Stack Overflow survey is big, has a lot of people in them, but they're all people who use Stack Overflow. So it's not universal of what software developers are. But the interesting thing is, in the results that just came out, is like for the third year in a row, Python is basically running up its game as the most popular software language. And that is because of two reasons. One is that Python is the duct tape of our entire CI infrastructure. And two is because of machine learning and big data. Python is the de facto language for machine learning. And there's a whole bunch of people doing it, and most of them aren't software developers. A lot of them are data scientists. A lot of them are in statistics. A lot of them do not come from a computer science background. And I've been helping quite a few of these folks, both in our company and just in general. Sometimes they wind up doing Java, and they wind up using my HTTP client because it's kind of the easier one to use. I worked with one psych major. She was working on a PhD in psychology and was slurping down Reddit and shooting whole discussion groups into machine learning and analyzing the patterns of white supremacy posts on Reddit. Really, really interesting stuff. And she's a psych major. And she's doing like machine learning and complicated computer science stuff. And I was like, wow, that's really cool. And she promised that she'd send me the paper once she's done. So, there's all these people out there, and we need to be able to kind of bring them into the fold. If there's people out there doing software development that don't look like software developers, I want them doing my software development because, again, a million jobs that are going to go unfulfilled. So don't look at that somebody needs to meet all of these requirements. So you look at me, I have certain aspects. People just assume that I have a computer science degree. I don't. I have a degree in community and regional planning from Iowa State University's College of Design. So I am a design and art major. I actually started off in school. I wasn't even started as a civil engineer and then downgraded to CRP. I started off with a fine art major. So I'm your second keynote speaker at this conference with an art degree, at least. And but I have all these other things. People look at me, and I started programming when I was 8, and I loved computers. I have a large selection of hoodies. I like sci-fi and fantasy, and I play role-playing games, and I meet all these stereotypes. And almost nobody ever even asks me if I have a degree. They just assume I do. But I don't. And the reason I don't have it is because when I got into college, I had a great fear of math, which I got over time. But I will blame our educational system for that. And of course, within role-playing games even, I play a female tiefling bard named Ronnie Spector Dio, which is not a normal thing for most people playing Dungeons & Dragons. So we need to look at all these different alternative education paths. I kind of naturally went into computer programming because it was my hobby. And that was a valid path for me. Now, I took seriously, and I've read most of the literature. I've read the SIS book and studied computer science on my own. And we can bring people into that. But we need to stop thinking of computer programming as being strictly something that needs to come from a computer science background. Computer programming is really more, it should be a blue-collar job. It should be a job that anybody can go into. You need a CS degree to do computer programming like you need a structural engineering degree to do carpentry. Is it nice? Yes, it does help. But it's not a requirement. And certainly there are lots of people who do it without it. I've worked with some amazing computer programmers that were music majors. I've worked with some amazing computer programmers who are architects, like building architects. You can come at it from a lot of different ways. So we need to be looking at alternative degrees, associate degrees, people who come from the military, coding boot camps. One note on coding boot camps is that it's a boot camp. Like I was in the Army. When I got out of boot camp, I wasn't going to go be Rambo and kill a bunch of people in the jungle, right? that takes, boot camp just gets you kind of primed. It lets you know what like the baseline is. We as a community are responsible for training those people up. And in fact, we as a community are responsible for training pretty much everybody. We need apprenticeship programs. We need to be bringing people in and training them. If you're not training people, if you're not bringing in green people and helping them become successful developers and DevOps people, then you're failing the entire community because, again, we don't have enough people to do this work. So one last thing I'll talk about in that diversity is the diversity of geography. We can't keep putting people in San Francisco in Northern Virginia. So I have a thing, my family and I, we drive around the state, and we have a little thing where we're going to every single county courthouse in the state of Iowa and taking our picture in front of it. That's Oskaloosa right there. These are all the ones we visited. So it's interesting as you drive around Iowa, rural Iowa, that you go from one of these county seats to the next, and one of them is really nice, and they have a beautiful town square, and there's people walking around, and they got ice cream, and then you go to the next one, and it looks like it's about 5 minutes away from being bulldozed. And the county courthouse has boarded up windows, and most of the town square is empty, and you just wonder, like, what's the difference? What's happened here? Why is that town okay, or seems to be okay, and this next town doesn't? I mean, a big part of the problem is that rural America has the same problem that Detroit has. It's massive depopulation. We've lost people. There aren't the jobs there. Manufacturing has gone away, and agriculture no longer requires nearly as many people to do it. And it's getting worse as far as, I say that worse, and I work for John Deere. But, we get demands that, people say there's not enough people to work on the farms. We need this automated. And eventually it's going to be almost entirely made up of robots. That's 20, 30 years down the line. It's going to be swarms of robots doing most of the farming in this country. And if you don't believe that, I actually know of at least 3 different companies in Iowa working on exactly that right now. So these are all the counties we've gone to in green, and we're working on getting the rest. These little towns, these nice towns, not every town is going to be able to become a tech hub. So some guys came out from Silicon Valley and went to Jefferson, Iowa, which is the county seat of Greene County, and there's now like this incubator, this tech valley, Silicon Valley incubator where they're doing mobile applications there. There's all these people that are out there, and these towns are cheap, man. You can live like a king or queen in a lot of these towns for not a lot of money. And some of them are really nice, and they've got a lot going on for them. I looked, here's a house, little Victorian in San Francisco, listed at 1.9 million, but the Zestimate is that it'll go for 2.5 million. You can have a nice mortgage of $9,000 a month. Now, and look at it. It's not even like that good. The paint's all chipped. Like, I don't gotta pay $2 million for that. And here's a nice Victorian in Waverly, Iowa for $154,000. You can go into these downtowns. You could buy out these beautiful little Victorian town square areas and have a beautiful little shop and have your coffee and everything, and everyone making a lot of money. And we're not taking advantage of this. We can be distributed, right? We showed that all this open source software is being written by these distributed groups of people. Why does everything have to be in San Francisco or Northern Virginia or Austin, Texas? And we've seen it moving into Des Moines, Des Moines kind of happening. The state of Iowa hasn't changed drastically in population. Des Moines is one of the largest, fastest growing metropolitan areas in the country. But the state isn't really changing all that much. And that's because we're draining rural areas, not just of Iowa, but of the entire country. And what we're left with are some of these towns which are beautiful and have a lot going for them and have beautiful parks and stuff. And we should be able to push that back out and make things more livable for everybody. So if you look at Waverly, this is where my family came from in like the 1880s. We showed up from Germany. We weren't farmers, but we were given a free farm because we showed up and we were white. And we just sat on the farm for a couple of years, the minimum amount, and then we sold it and we opened a bar. And, and so we owned bars in Waverly, Iowa for many, many years. This is me in front of the plot of land that we were given for free when we showed up in 1880. Waverly's got a nice little college there. Wartburg College has beautiful like river view. Why not have a startup there? Why not have an incubator there and hire different kinds of people, people who are in the rural community? What about somebody, again, we don't have to have young people necessarily. We can train. Programming is actually pretty easy, especially most programming is pretty easy. There's very little programming that's actually super, super hard. We do some of that at John Deere, but the vast majority of programming I've done over my life is not that difficult. What is difficult is running systems and keeping them up and being able to evolve them. And that takes collaboration. You can't do that alone. So let's bring in someone who was laid off from their manufacturing job. Let's bring in someone who took time off to raise their kids and are now trying to look to get back into a job that's supposed to be really good and supposed to pay really well. And can we do that in areas where we can actually keep our costs down? So that's really the challenge I give to you. Like how do we solve this problem of too much complexity and not enough people, and go back and think about how, because you're going to have to deal with this whether you want to or not. So sleep on that for the weekend. Thank you.